Hello, so today we're going to talk about the Maclaurian series. The Maclaurian series is an infinite series of powers of x. But what is a series? A series is what we obtain when we take the sum of all the terms in a sequence. Okay? Examples of a sequence are such as below. This is a sequence with first term 3, second term 8, third term 13, and so on. Another example of a sequence is this one where the first term is 3, the second term is 0, the third term is minus 3, and so on. These are all both are sequences that are examples of sequences that proceed to infinity. And the idea of infinity can be described as follows. Since there's no largest natural number n, no matter how large a natural number, we can always add 1 to obtain a larger natural number. This idea is represented by what we call infinity. Therefore, it is possible to conceive of an infinite sequence, such as the examples of the given above. So now back to our original question, what is a series? A series is what we obtain when we take the sum of terms in a sequence. Okay, so for example, this 3 plus 8 plus 13, this is examples of series obtained from the sequences above. Now to our original question, a power series. It may be that we want to represent a function as a series of powers of x. This can be very convenient to do, and it is also not very difficult. So as an example, suppose we wish to express sine of x as a series of powers of x. Then we can write sine of x as equivalent to a plus bx plus cx squared plus dx cubed plus dx power 4, and so on and so on, where a, b, c, and d, e, and f are constant coefficients. Notice that we have used the equivalent sign, not the equal sign, to show that this is an identity, not an equation. Therefore, the expression is true for any value of x we like to substitute. And now take as an example, we substitute x equals 0. This gives us a equals 0 because the substitution x equals vanished all terms except the first term. So we see that this way we have been able to find the first constant coefficient a. Now, is there any other such substitution that can lead to all terms vanishing except the second term? This is not directly possible, but we can differentiate both sides just first and then substitute x equal to 0. Once we do this, we find that all terms vanish the right hand side except the second term, therefore b becomes equal to 1. Our passes now has a and b defined, and we can write it as such. Repeating this process to find c the same way, differentiating then substituting x equals 0, we'll find c equals 0. Again the same way, we'll find d equals minus 1 over 3 factorial. Again the same way, we'll find e equals 0. Again the same way, we'll find f is equals to 1 over 5 factorial. Now we see that by this method, by the repetition of this method, we have found the constant coefficients a, b, c, d, and so on. In this case, we have found up to f. Therefore, our power series of sine x can be written as x minus 1 over 3 factorial x cubed plus x power 5 for 5 factorial, and so on. We have obtained, therefore, the infinite power series representing the function sine of x. And we can see the pattern to form the subsequent terms. Now, to establish the Maclaurian series, we use the process from the previous example, but we now work with the general function f of x. Okay, so let f of x be equivalent to a plus bx plus c x squared plus dx. Okay, then substituting x equals 0 at the first instance, we'll be able to find a, which will be equal to f of 0. Okay, and then differentiating and then substituting x equals 0, we'll find b equals f factorial f dash of 0. Again, repeating this process, we'll find c equals f dash dash of 0 over 2 factorial. Again, repeating this first, we will find d equals f dash 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 of 0 over 3 factorial, and so on. So therefore, we have the general Maclaurian series, which becomes f of x equals f of 0 plus f dash of 0 x plus f dash dash of 0 over 2 factorial x squared plus f dash 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 of 0 over 3 factorial, and so on and so on. This is now the established Maclaurian series.
Okay, so next we go to applications. The Maclaurian series is very important because it can be used to turn complicated continuous functions like sine of x, e of x, ln of x into simple polynomials. Okay, so the Maclaurian series can be used to approximate function values and enable computers and calculators to numerically compute these values. A computer cannot directly evaluate, for example, the sine of 0.1, nor does it store the whole of the mathematical tables. So this will not be feasible. So therefore, instead, what a computer does, it uses the first few terms of the Maclaurian series to approximate that function. The more terms used, the greater the accuracy. We will demonstrate this by writing a simple computer program in C++ to calculate the value of the function ex. We know that the Maclaurian series for ex is given that you can use the Maclaurian series obtained above to find the Maclaurian series representing the function e of x. And then now in turn we'll use this series to find e of x, to program a computer to find e of x. That will be our next task, to show the application for the Maclaurian series. Okay. see right now.